Greetings, fellow aliens. You might wonder why I haven't posted any episode for a while. The answer is simple: relativity. I made a trip with 99.5% light speed. The trip lasted about 1 moon cycle for me, but 10 moon cycles for you. But now I'm back, with a new episode about a strange and peculiar earthling science, mathematics. Earthlings thrive for knowledge is driven by several factors, like curiosity, doubt, warfare, show-off, and laziness. The latter, laziness, is what gave rise to mathematics. We will come back to this later. In a nutshell, mathematics could be called science of truth. To understand this notion, we have to understand the earthling concept of true and false. In other words, earthling logic. If you are an alien, you are probably familiar with the common fuzzy ternary logic. Statements can have the values true, false, don't know, or anything in between. This is often represented as the uncertainty triangle. For those unfamiliar with ternary logic, allow me to explain. Imagine a centauri lottery. You have a box of 6 creatures, tribbles and snorks, and you draw one of them, hoping to get a triple. Now, the claim, "I'll draw a triple," will be true if you know that all the creatures are triples. If they're only snorks, the claim will be false. If you have 3 tribbles and 3 snorks, the answer is halfway between true and false. If you have no idea what's in the box, the value is don't know. When you know that there is 1 tribble and 2 snorks but don't know what the rest is, the value will be somewhere within the triangle. Of course, this value depends on what you know. When you gain information, the value moves away from the don't know corner. That is, in a nutshell, the uncertainty triangle. Many alien races only know the 3 corner values and don't care about intermediate values. Political logic is the opposite. The corners of the triangle are cut off. An alien politician will never clearly say something is true, or false, or admit that he doesn't know. Well, he might say that he didn't know. This logical value is called plausible deniability. Not everything fits into this schema, though. The administrative logic used internally by the Central Galactic Bureaucracy, for instance, has 11 values: approved, rejected, wrong form, bring more documents, file lost, not this desk, this will take some time, awaiting cash, nothing I can do, incorrectly stamped and desk closed, come back later. The administrative logic is one of the reasons nobody really knows how the bureaucracy works. Space squids, on the other hand, have a unary logic based on one single value, bloop. The actual information is transmitted in the nuances on how the bloop is pronounced. It's a bit like the earthling word awful, which can mean very good or very bad. Now, earthling logic is binary. Earthling brains are composed of cells called neurons which have only 2 states, silent and active. Likewise, earthling logic is based on 2 values, false and true. There is no middle ground. Earthlings believe that all claims have a value true or false, and when you see neither of them, it's only because the actual value is hidden. Earthlings call this imaginary hidden value truth. By the way, this binary thinking is the reason why earthlings have such problems wrapping their mind around quantum physics. Their brains can't accept the idea that, for example, 2 different realities can coexist as long as they are not observed. If we combine binary logic with the earthling concept of things, we get set theory. A set is a collection of elements, mathematical entities that may stand for any kind of things. Elements are either in a set or outside. Earthling logic knows no middle ground. The earthling logic leads what earthling call conclusions, rules for combining claims to get new claims. Conclusions are what the fabric of mathematics is made of. We will come back to that point. But the roots of mathematics lie in a very practical problem, counting, or more generally measuring. Let me elaborate. Every young planetary civilization has to find a way to measure resources, population, arable land, food, real estate, raw materials, time. All this needs to be properly measured. Also, construction requires measuring quantities like lengths, areas, volumes and angles. Small quantities can be measured directly, but things get more complicated when the quantities are either bigger or not easy to measure. That's when calculating comes in. It's a shortcut, a way to combine available quantities to get other quantities. In other words, calculating is measuring times laziness. Every alien race has its own calculating methods. The old Aberranians, for example, use a curve to multiply values. It's a strange method, but it works. Now, the bigger a civilization becomes, the more things are to calculate. That's usually the point when a planet's bio-administrator gives the civilization limited access to the great galactic grid, and thus to planetary superbrains which do the calculation work for the whole galaxy. The access to superbrains is completely free, at least for some 100 solar cycles. But once the civilization is completely dependent on external computer power, a tax star portals into orbit and the planet becomes full tax-paying member of the galactic bureaucracy. At this point, they don't have much of a choice. The computation monopoly of the planetary superbrains make them one of the powers that run the central galactic bureaucracy, alongside with the tax authority, the control bureau, the apparatus, the galactic intelligence, the space force, the committee, the galactic bank. Well, it's complicated. Actually, nobody really knows who pulls the strings in the galaxy. But mankind had no bioadmin and no access to superbrains, so they had to develop their own way to deal with computations, mathematics. Basically, mathematics is a way of avoiding calculating, and calculating is a way of avoiding measuring and counting. That's why we could define mathematics equals measuring times laziness squared. Tips for tourists. In general, Earthling books are an interesting and exotic souvenir. However, mathematics is considered counterband by galactic laws, because it threads the computation monopoly of the superbrains. You don't want to run into a hyperspace patrol with a math book on board, it could get you into serious trouble. The first contact of aliens with mathematics goes back many millennia. More than 4,000 solar cycles ago, a couple of alien information smugglers landed in a region called Egypt, and offered the Earthlings advanced computation methods and the exact value of pi, in exchange for the recipe for beer. The Egyptians politely declined. Their computation methods were sufficient to build huge pyramids, not to speak of the logistics required to pay and house thousands of workers and to move millions of tons of calcium carbonate. As for pi, they had already incorporated pi into the dimensions of some of their pyramids, using rolled and stacked cylindrical barrels. To construct their pyramids, the Egyptians had developed something called geometry, the theory of shapes. In a nutshell, geometry is all about lines, angles, and areas, and how to avoid measuring them. The information smugglers came back 1,000 solar cycles later, this time in Babylonia. But the Babylonians were not impressed. Their mathematicians knew the Pythagorean theorem, could solve quadratic equations and were able to compute the square root of 2, with an error of 1/10,000th. More generally, the Babylonians had developed the art of manipulating numbers. Earthlings call this arithmetics. What are numbers? Well, it has to do with things. To quantify things, Earthlings invented numbers, a series of abstract things, called 1, 2, 3, 4, 5, 6, 7, etc. Think of numbers as a series of imaginary stickers. Whenever Earthlings want to quantify things, they glue the stickers onto them, one by one. This is called counting. The last assigned sticker indicates the quantity of things, their number. Earthlings are obsessed with numbers. They count and number everything: houses, offspring, vehicles, books, even kings, and gods, everything. Except for the microbes. There are many ways to represent numbers. But the most common way is the decimal system. Numbers are written as series of digits, 9 of them correspond to the numbers 1 to 9, and an empty digit called 0. The 10 digits come from the fact that Earthlings have 10 fingers, the bony tentacles at the end of their upper extremities. Some ancient civilizations used a base 12 system or a base 60 system, which are more useful for divisions. You'll still find remains of both systems, in particular for measuring time. Earthling computers use a base 2 system, as they are based on true-false logic, not on true-false don't-know logic like most alien computers. By the way, squids have a similar system, but it's a base 1 system which contains only the digit 0. Any number above 0 can't be expressed in this system and is called sum. The Earthlings found numbers quite useful, and when Earthlings find something useful, you can bet that they want more of it. For starters, they took the digit 0 and made it a number, closing the gap below the 1. Generally, Earthling mathematicians don't like gaps. For example, when you subtract 5 from 2, you fall into a gap below 0. So, Earthlings invented negative numbers. Likewise, when you divide 5 by 2, you fall into the gap between 2 and 3. So the Earthlings invented fractions, aka rational numbers. Those numbers can be represented as a nice straight line. In ancient Egypt and Babylon, mathematics was just a set of practical rules, a toolbox for architects and bookkeepers. But this approach was about to change. About 2,300 solar cycles ago, our alien information smugglers came back a third time, again in Egypt. Here they met a Greek mathematician named Euclid who had developed a wholly new approach to mathematics, axioms. Realizing they had nothing to top that, our aliens left, never to return again. But what are those axioms? Well, axioms are fundamental assumptions you build a theory upon. Take, for example, the natural numbers 1, 2, 3, 4, 5, etc. Those numbers can be described with the so-called Peano axioms. There is a number called 0. Every number has a successor. 0 is successor of nobody. No two numbers have the same successor. If a property holds for 0, and it propagates from each number to its successor, then it holds for all numbers. This is called induction. Given any set of axioms, you can use logic to construct a whole building of conclusions. Interesting conclusions are called theorems. That's basically how the whole of modern mathematics is built. Note that mathematicians don't think axioms are based on truth. They are just assumptions to start with. Mathematicians like to play with axioms, omit this one or add that one, and see what happens. Note that mathematics never says that is true, but rather given this and this, you can conclude that. In other words, mathematical theorems are always true, because they are elaborate tautologies. One could define mathematics as hunt for interesting tautologies. This is the theoretical side of mathematics. There is still the practical one. Measuring times laziness². Now, according to mathematicians, doing mathematics is not so much constructing into the sky as it is exploring an unknown territory. You have to construct the roads and bridges, but the landscape is already there. So, let's explore a bit the landscape of mathematics, shall we? At the very center we have basic logic, and the two disciplines geometry and arithmetics. As said before, geometry is all about shapes and measures, and arithmetics is all about numbers and operations. This is the starting point for the exploration of mathematics. Starting from here, we will discover several regions of mathematics, number theory and algebra, which are derived from arithmetics, topology, which comes from geometry, and analysis, which is arithmetics used to measure geometry. Let's start with topology. Topology is, so to speak, geometry minus measuring. It's kind of rubber geometry. It considers properties of shapes that don't change when you deform them. If you explore the properties of natural numbers, you get to number theory. Number theorists are particularly fond of prime numbers, numbers that can't be broken down into smaller factors. Now, arithmetics can be further generalized, with a little trick mathematicians are fond of. First, you take an example, say, the natural numbers. Secondly, you state some basic rules. And third, you forget about the example and consider those rules as axioms. This is exactly how arithmetics is generalized into algebra. For example, adding can not only be applied to numbers, but also to other things like arrows, spatial movements, permutations, rotations, or even dancing steps. Roughly speaking, when you generalize the rules for addition, you get semi-groups. When you include subtraction, you get groups. When you allow multiplication, you get rings. And when you make sure you can divide, you get fields. This belongs all to the domain of algebra. In a certain manner, algebra is all about manipulating symbols. Scientific advice. If you are a xenobiologist, you probably know bloblings, jellyfish-like creatures of various shapes. Now, the classification of bloblings is basically a problem of topology, but you can do it using group theory. In other words, adding and subtracting. See, bloblings are into what Earthlings would call bondage. They like to wrap closed rubber bands around their body. There are countless bondage methods, but you can define addition and subtraction between bondage loops. This loop plus that loop is that loop. Or that loop minus twice this loop is that loop. Now, for this particular blobling, all bondage variants can be obtained by combining two loops, through the hole, and around the hole. Mathematicians would say it is a group of rank 2. Other bloblings need for loops, or 6, or 14. This number doesn't change when we deform the blobling. That's something topologists really like. So, this number can be used to classify the bloblings. If this was a bit too much for you, don't mind. The important thing here is that we can use algebra to solve problems in topology. This domain halfway between topology and algebra is called algebraic geometry. Algebra is a bit like what Earthlings call magic. You manipulate some symbols and apply some formulae, and suddenly you have performed something completely unrelated. One could say that any sufficiently evolved algebra is indistinguishable from magic. This holds even more for another discipline, category theory. This theory is all about stuff connected with arrows. It looks like fiddle-faddle but is surprisingly useful. Mathematicians call the use of category theory in other disciplines abstract nonsense. I'm not joking, it's called like that. Abstract nonsense. Now, we have seen two big regions of mathematics, topology, which is basically geometry minus measuring, and algebra, which is arithmetics minus numbers. A third big field of mathematics takes the numbers from arithmetics and uses them to measure geometry. This is called analysis. To understand analysis, we first have to understand something else, infinity. What's infinity? Well, it's another gap filler. When you count and count onwards, the numbers actually go nowhere. So mathematicians invented a number behind all natural numbers, infinity. Once you have the concept of infinity, you can observe, for example, infinitely long increasing sequences of numbers. Some tend to infinity. Others approach some rational number. But there are others that approach nothing, that fall into a gap. But mathematicians don't like gaps. So they defined a new kind of numbers to fill the gaps, real numbers. A real number is anything that can be approached by an infinite sequence of numbers. Now, real numbers are very useful to measure things, lengths, angles, areas, time and so on. Analysis is particularly interested in functions, measures that change over time. This leads to two things, accumulated values, or integrals, and change rates, or differentials. Turns out that the one is actually the inverse of the other. That's the fundamental theorem of calculus. Analysis has many practical applications in engineering and natural science, particularly physics. We will speak about earthling sciences in another episode. Strategic advice. When attacking a planet, a common tactic is to cut off the defender from the great galactic grid, to block all ballistic computations. However, Earthlings' artillery doesn't need to access the grid, they use mathematics. So you better anticipate precisely aimed artillery fire. With real numbers, mathematicians have filled most of the gaps. But one gap remains, there is still no square root of -1, or any other negative number. So mathematicians invented a square root of -1 and called it I. They didn't quite know where to put it, so they put it above the line. This new number, and everything you can create by combining real numbers with I, are the complex numbers. Back to our mathematical landscape. Like between algebra and topology, there are interdisciplinary fields between analysis and the other fields. When you combine analysis with topology, you get differential geometry, the theory of shapes with notions of length and angles. It's very useful, for example for speculating about the shape of the universe. On the border between analysis and algebra we have algebraic geometry, the theory of shapes defined by polynomials. One example would be this heart-shaped surface, which is defined by this equation. Earthling viewers, feel free to forward the formula to mathematically inclined reproduction partners. I understand Earthlings like to do such things. I don't know why. It's probably a ritual. There are many other mathematical disciplines, for example probability theory. It's basically an extension of binary logic to the whole true-false edge of the uncertainty triangle. Earthlings think that even uncertain claims are somewhere between true and false. There is still a whole dimension missing, but it's already an improvement. I will conclude with a theorem that doesn't belong to the fields mentioned above. It's rather out in the ocean of logic and metamathematics. I'm speaking of Gödel's first theorem. It's closely related to Earthlings' true or false logic. See, most mathematical claims in a theory can either be proven true, or proven false. But Gödel constructed a claim that says I can't be proven. The claim can't be false, otherwise it would be a false provable claim, and that would be nonsense. So, according to Earthling logic, it must be true. But if it's true, it is right about being unprovable. So we have a claim that is true, but you can't prove it within the theory. In other words, mathematics can prove a lot, but it will never be able to prove or disprove everything. There will always be open questions. This was the 13th episode of Earthlings 101. The next episode will be about the two thinking systems Earthlings have, intuition and reason. But before that, I'll have to make the third and last episode of my Nudge series about the shape of the universe. Subscribe if you don't want to miss it. Thanks for watching, and as always, don't forget to be alien.